Okay, so we need to wrap up this little bit we have still left on polynomials. I mean, I pretty much told you everything last time. There's really not much left, but just I want to make sure, because I was a little bit hurried, that you get the message about complex roots, right? So if you have, right, if p of x equals an x to the n plus a1x plus a0, right? And if c is alpha plus I beta such that p of c is equal to 0, right? In other words, suppose you have a complex 0 to a real polynomial equation. What does that mean? That means that you like plug it in, right? an alpha plus I beta to the n power a1 times alpha plus I beta plus a0, all of that is 0. Like when you plug it in, it gives you 0. All right? But here's the thing. If you study the properties of complex conjugation, like the complex conjugate of a sum is the sum of the complex conjugates, and the complex conjugate of a product is the product of the complex conjugates. So what that means is if this equation is true, then you can take the complex conjugate of it, right? And so since an all the way on down, a1 and a0 are real, it follows essentially by definition that the complex conjugate of an is an, and so forth and so on down the line, right? They're real coefficients, so they're unchanged under complex conjugation, right? So what that means, right? What that means is if I take the complex conjugate of this equation right here, right? What do I get? I get an alpha minus I beta, because that's the complex conjugate, all right, to the n, a1 alpha minus I beta plus a0 equal to 0. But what we're looking at here is nothing more than like taking the polynomial p and evaluating, plugging into it alpha minus I beta, right? But that's by definition the complex conjugate of the root I started with, c bar, right? And so we see that's equal to 0. So this is, I claimed this last time without proof, that if you have a real polynomial equation, if you have a complex solution, they have to come in conjugate pairs. That follows from this calculation right here. You just take the complex conjugate of what you have, and you get the same equation, but with complex conjugate replacing the complex number. Notice that this only works because the coefficients of the polynomial are real, right? If you had a complex polynomial, you could have other things, right? Like if you had, for example, if you had something like p of x is equal to x minus 2 plus I times x minus I. So here, what would the roots be? The roots would be, you have root 1 is 2 minus I. You have root 2 is I, right? These are not a complex conjugate pair, but that's also not surprising because if you multiply this out, what do you get? A mess, right? But the point is, this is x squared, and then if you like gather all this junk together, oh, those cancel. That's kind of funny. That's a very, if I wanted that to happen, it wouldn't have happened. Oh man, that's weird. Look at that. Funky. Oh, that is wacky. Ooh. Okay, let me not dwell on that. That's really interesting, but not for this course. Anyway, maybe I made an arithmetic mistake, but my point is, you've got a coefficient which is complex, right? All right, I was trying to buy some time for the student who's missing. This is really kind of like not something I'd usually present, so I will stop with the, rabbit chasing here, and get back down to business. So, what was our next example we had? Reverse example time. I said I want you to find a polynomial of least degree. All right, so here's the problem. Find a polynomial of least degree. So this is ICE 1.6.25. Right. P of x such that, what are the features we want for this thing? We want P of 1 to be equal to 0. We want P of minus 3 to be equal to 0. What else do we want? We want P of 3 plus 2i to be equal to 0. All right. And we also want P of 0 to be equal to 7. Now that's kind of a different animal. And you're supposed to leave it in factored form. All right? So, we don't often ask you guys these kind of questions, but we should do it more. What happens in math? Usually like, here's a polynomial, factor it, right? So I'm asking you the opposite question. Construct for me a polynomial which has these things as zeros, right? So what we're going to do, let's say, where's my eraser? Here it is. I think I need to wash this. It's starting to get kind of dusty. So remember the theorem we found last time? If we have, how's it go? P of alpha plus I beta equals to 0 if and only if what? X minus alpha squared plus beta squared is factor in your polynomial P of x, right? So look at this. This is alpha equals to 3, right? Beta equals to 2. So what does that suggest to us? That suggests this one gives us a x minus 3 quantity squared, right? Plus 4 factor. That's a factor in our P of x. Now, basic factor theorem, this one gives us what? This gives us an x minus 1 factor, right? How about the minus 3, P of minus 3? If that's a 0, what's a factor? X plus 3, right? And so the instructions, which I didn't write down, but I read, was find a polynomial of least degree that does these things, right? So that's going to be degree 4. And it looks like this, right? P of x, it's got what? It's got your x minus 1, you got your x minus 3, you got your, and you could multiply this out if you want, or you could leave it like that. It's really up to you. I mean, this is totally fine in my book. In some sense, that's to be preferred to the multiplied out version. Why? Why is this, in some sense, better than that? Why is that? What's better about the completed square version of that quadratic factor? I would argue the thing that's better about it is you can just look at it. You look at this and you say, can I factor x squared minus 6x plus 13? I mean, without further thinking, I don't know, right? But if I look at x minus 3 squared plus 4, I know immediately that cannot be factored over the reals. It's irreducible. it's in your face, right? It's manifest. So what's the one piece of information we haven't used yet, and how can it be used? So we have not yet used that the y-intercept of the polynomial is 7, right? But what's the other freedom we have in factoring a polynomial? We can also choose the leading coefficient to be whatever, right? Almost all of my examples have had a leading coefficient of 1, but that's just because I'm lazy, right? I mean, you could put an a here. Doesn't change anything. But now, you see, we have the annoying problem of figuring out what does a have to be in order that p of 0 is 7. So what do? Plug it in. Yeah. Plug it in, plug it in. Isn't that I feel like that's a commercial. So that's 13. So apparently, and that's all equal to 7, right? So therefore, a is equal to 7 divided by 39. So you take that, right, and you plug it back up in here, and that's your answer. That's the polynomial that's desired. Now, if people didn't tell you, if the problem didn't say p of 0 is 7, what would the answer be? The answer would be there's an infinite family of answers, but they're all like just multiples. Like you could put any number here, and that just shifts the kind of compresses or stretches the graph out. But if you compress or stretch the graph of a polynomial vertically, you don't move the zeros. They just kind of stay in place and the thing stretches out. So where the zeros are is independent of where you put that thing. So anyway. 3 times 13. Oh, the 13 is this. When you plug in 0, you get 9 plus 4. But to be honest, I looked up here. Because like when I plug in 0 into a quadratic, it's the constant term. So you could, I mean, you got choices. All right. So the fundamental theorem of algebra says what? It says any polynomial with real coefficients can be factored into a product of linear factors, possibly repeated, and a product of irreducible quadratic factors, possibly repeated, right? This is the fundamental theorem of algebra. It says we can always, at least in principle, factor any real polynomial into a product of linear and quadratics, right? So as we're thinking about solving problems this semester, if we can talk about how to solve the problem for like a linear factor and for a quadratic factor and products of those things, that means we've covered everything. It's just something to think about as you go forward in calculus. Or I mean, more, I'm just saying something to think about if you think about what are all possible cases to consider, right? Like it's enough if you consider factorization in terms of products of linear and quadratic like that. That's all you got over real polynomials. I have a few examples in the notes I'll let you guys look at. Let me talk about, so I'll let you look at examples 27, 28, and 29. I want to talk about Pascal's triangle, and that'll be it for polynomial techniques. Have you guys heard of Pascal's triangle before? You have? Don't remember it? Remember being talked about. Okay. Here, let me write down some identities. So like a plus b squared, what is it? It's a squared plus 2ab plus b squared, right? A plus b cubed, well that guy is, a cubed plus 3a squared b plus 3ab squared plus b cubed. All right? A plus b to the fourth is a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. These are special forms, right? Now, whoa, I should not, this thing is not good. I said you don't have to wear your mask, but you might consider a mask in here just for the chalk test. Joking. See here, so Pascal's triangle is this. You start with a 1, all right? Then you go 1, 1, 1's here, 1's here. 1 plus 1 is 2. 1's on the outside always. 1 plus 2 is 3. 1 plus 2 is 3. 1's on the outside. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. Right? Next. 1 plus 4 is 5. 4 plus 6 is 10. 4 is 10. 4 plus 1 is 5. 1. So as you go down, you're going to go 2, 3, 4, 5, 6. Right? Now, so if you do a plus b to like the n power, it's the sum k equals 0 to n of n, choose k, a to the n minus k, let's say, b to the k. So this is read n choose k. You'll study this again in your statistics course, or where you talk about counting and probability. So like n choose k is the number of ways of choosing k things from n things without repeats. It also, these are also the so-called binomial coefficients. And the binomial coefficients are exactly the numbers which appear in Pascal's triangle. So like here, you're multiplying this by like, how many ways? 4 choose 0. Here you're looking at 4 choose 1 as your coefficient. 4 choose 2 as your coefficient. 4 choose 3 is your coefficient, and 4 choose 4. So this row right here, that's 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. There's also a formula for this n choose k things in terms of factorials. Let me not say that at the moment. I don't remember it off the top of my head. I'll mess it up. Really, my point is you don't need to remember the formula because you can just kind of read it off Pascal's triangle for the kind of small examples you'd be tempted to use this for. So let's just take the next step. How about a plus b to the fifth? See, what this formula says is you start out at the nth power for a, and then it steps down as k increases. It goes for like n, n minus 1, n minus 2, all the way down to n minus n, which is 0. So like the last term in the sum doesn't have an a thing. It's just got a b thing, right? So notice how the power of a steps down as the power of b steps up. And the binomial coefficients tell you how to weight the thing. So I'll start it out. A to the fifth is the first thing. Then what plus? 5, a to the fourth, and then, so a decreases, b increases. So b, then I got this 10, a cubed, b squared, right? Another 10, a decreases, b increases, to cube this time. And then I got a 5, right? So like the bookends to these are always kind of symmetrical, right? And then what's the last thing? Last term is b to the fifth. So there's how you can remember a plus b to the fifth power using Pascal's triangle. You just follow the pattern. Mm-hmm. Now, of course, if you're on a desert island and you have sufficient paper and pen and pencils and stuff and you got time on your hands, you could also just multiply this stuff out. There's nothing stopping you from foiling and distributing and collecting terms, right? But goodness gracious, this is way, way faster if you know it. And sometimes we're just interested in the general pattern, all right? Like we will soon be talking about differentiation. And so we might want to expand like x plus h to the n power, right? So looking ahead a bit, we'll do something like x plus h to the n power. And see with the binomial coefficient, binomial expansion, we already can tell you what that looks like. It's like x to the n plus n, x to the n minus 1, h, and then stuff. Until all the way you get to h to the n, see? That's actually a calculation we'll do in about a week or 2, 3, I forget. But you see, the fact that there's an n here, that's like just this. There's always an n when you expand a plus b to the n power, like the next coefficient is n. A plus b squared, there's a 2 here. A plus b cubed, there's a 3 here. A plus b to the fourth, there's a 4 here. There's a 5 here. There's an n here. All right, so half of your in-class example was to copy Pascal's triangle from the board. The other is to factor x cubed minus 6x squared plus 12x plus 8. So how are you going to do that? Oh, I remember. He had like a freshman seminar. That's what it was. He told me yesterday he had freshman seminar. I don't know why I'm looking for him. I'm an idiot. They schedule freshman seminars at the most annoying times in the semester for people.
Oh, you mean like an actual seminar? I thought you meant the class.
I don't know, but I've had this problem before, so I assume he's telling me the truth. So let's see here.
He might know for sure, honestly.
Well, I wouldn't be able. Blind leading the blind if I tried to help him. So this is a problem we can solve with Pascal's triangle. If you look at this as what it is, right? This is x cubed plus 3 times what? Times minus 2 times x squared, right? Plus 3 times minus 2 squared times x. Oh, man. Seriously? Oh, I copied it down wrong. Thank you. Whew. That's a minus. That's good, because if that's not a minus, my instructions are totally bogus. With a minus there, then we can write plus minus 2 cubed, right? See what you're looking at? You're looking at the pattern. A cubed plus 3, a squared b plus 3 b squared a. I'm writing it weird, sorry, plus b cubed. In other words, that's a plus b cubed. So hooray, we have factored it. It is x minus 2 cubed. So, all right, so if you can factor a polynomial using one of these like Pascal's triangles, it's a kind of special one, right? But these examples do exist and they pop up in applications and things. It's worth being aware of. There it is. All right, so that brings us to the sign chart method to solve inequalities. All right. So let's see here. I'm going to let you read. So basically, I define an algebraic critical number as a place where either the formula is 0 or it's not in the domain of the formula, all right, or it's a boundary point of the domain. And what I say is essentially to solve where the expression is positive or negative, you just draw a number line and put all those critical numbers, those algebraic critical numbers, and then test points in each region to the side of those points, and you'll be able to solve the inequality in this way. Here's an example. So here's the ice 1.7.4. So we've got x squared plus 3x times x squared plus 4x plus 5, all right, divided by x squared minus 2x. And we're supposed to solve this inequality, figure out where it's less than or equal to 0. Solve this inequality. So now we're going to get to put into practice all that factoring we've been doing so far, right? Because in order to figure out the algebraic critical numbers of this expression, we need to see where is the expression, the numerator. If the numerator is 0, the expression's 0, right? If the denominator is 0, we're in trouble, right? So those are either one of those cases is a place where the sign of the expression can flip to positive to negative, right? So how do we figure out where the numerator and where the denominator can be 0? Well, we should factor. Factoring will reveal it. So the numerator, you've got x times x plus 3. We can complete the square on that guy. That is x plus 2 quantity squared plus 1. Completing the square right there. And downstairs, we've got x times x minus 2. Right? So we're trying to solve this less than or equal to 0. So our algebraic critical numbers are thus x equal to 0, minus 3, and 2. This guy is always positive. The smallest this can be is 1. So this cannot contribute to a sign change. It's just always positive, right? Yeah, any of you guys have friends like that? They're just always positive? Doesn't matter what happens? Those friends are hard to find, aren't they? It's a lot easier to find people that are like always negative, I think. Especially in college. Yeah, I mean, well. All right. Delete. Okay, all right. Sorry, I have to be careful what I say. Minus 3, 0, and 2. So I mark these down, and then just test a point in each of the subregions, you know? Like, so if I plug in, like, say, minus 4, what happens? You don't actually have to figure out the number. You just need to figure out the sign. So plugging in minus 4, I get like a minus 4. Well, these guys are going to cancel, right? So actually, except for x equal to 0, you could just cancel these. So I've got minus 4 plus 3, which is minus 1. This is positive. So I've got minus 1 over minus 6. So it's a net positive. So it's positive over here. How about if we plug in minus 2? Or you could, you could plug in minus 1, whatever. If I plug in minus 2, I get this is positive, that's negative, so I get minuses up in here. If I plug in 1, positive, negative, still negative. If I plug in 3, well then both of these are everything, pluses all around, pluses. So what was the question? The question was to solve this inequality, right? So what's the answer? We should do minus 3 to 0. And, okay, so now my question's a little bit harder. Is minus 3 included or excluded? Is minus 3 part of the solution? Does it give you less than or equal to for this expression? I hear, yeah, right? It makes the numerator 0. It gives you 0. So we can include minus 3. It's okay. 0, on the other hand, is not allowed because you have division by 0. 0. So 0 is not in the domain of the expression. That can't be included. And then 0 to what? To 2. What about 2? Is 2 included or excluded? Well, we got to exclude 2 because we got division by 0 at 2. So there you go. That's the solution to this inequality. I know this inequality looks kind of scary at the start, but actually we can solve these kind of inequalities if we can factor the pieces and just take it apart, draw the sign chart. We can easily solve pretty much any inequality you face involving a rational function. It's not really that hard. We just have to factor the pieces. 2 is excluded. I'm trying to make it one of these guys. I know I try to make these really pronounced, when it's included. But. So that's it for chapter 1. That's pretty much all I've got to show you. Everything else is storytelling. I mean, there is interesting storytelling to do. You guys, we looked at the quadratic formula, right? So you know the formula for this, right? You can solve it. We did. It wasn't a big deal, actually. It was like relatively simple to find this formula. Every high schooler should be able to derive this for themselves. That should be an expectation of like the 11th grade or something. If your education system is doing what it should. That ought to be expected of people. If you're an Algebra 2 student and you can't derive this, you shouldn't really be, that is something that should be expected of Algebra 2 students. Like seriously, not joking. When my wife was in high school in Hong Kong, she was in an advanced math class. They actually studied the cubic and the quartic equations. Do you know what those are? So like the cubic equation, same thing. That's the cubic. The quartic. So here's the cubic, here's the quartic, right? Now, various European mathematicians, Tartaglia, Ferraro, something like that, Italians back in the 1500, somewhere in there, they found formulas for solving the cubic and for solving the quartic. All right? And you can actually study those in a high school algebra class. If you got an advanced class, like you could do it. It's hard, it's not easy, but formulas are known. I mean, the formula is like a page long, roughly speaking. Okay? Now, of course, we can factor those for certain examples, right? But every factoring example that I've given you, it's come with like a hint or some sort of obvious feature. So like the factoring went out nicely, right? If we know one of the zeros, then we can kind of like divide that out, and that makes it knowable, right? Here's the interesting thing. So about 1700 or so, this mathematician Euler, at that point they had written these like giant books of algebra, and it was starting to, like all the university students knew kind of the notation we know, and they were looking at it. And so, of course, if you found the equation for solving the cubic and solving the quartic in terms of, and it's also in terms of radicals like this, okay, cube roots and stuff, it's natural to think that this can continue, right? So maybe you can find an equation for solving the fifth order problem, the so-called quintic, in terms of radicals of the coefficients, right? So the great mathematician Lagrange who's also the one who's, like, if you've ever heard of Lagrangian mechanics, how modern physics is done. But anyway, Lagrange spent the better part of decades systematically searching for this quintic equation, right? And more or less after Lagrange did his things, people started going, ooh, if Lagrange can't solve it, and Euler didn't solve it, maybe there isn't a quintic equation. So then it fell on early 19th century mathematicians, Abel and arguably Ruffini, to prove that there did not exist a quadratic formula for the quintic problem. But then this fellow named Galois, he's French, it's spelled like this, invented something that's based similar. So we saw that the complex conjugate roots come in pairs. So that there's kind of like a symmetry between them, right? So Galois generalized that idea to say that there's a symmetry between the roots that solve a polynomial equation. Like you can rotate the roots amongst each other in some sense, some abstract sense. And he found something called a group that you could calculate for a polynomial. And he showed that for certain kinds of groups, it was impossible to find a solution by radicals. And then for others, it is. So some quintics, you can find a formula in terms of radicals, others you can't. And that was the birth of what's called group theory in about 1830. And so mathematicians are still studying group theory to this day. This is like active area of ongoing mathematics. But these stories all go back to just basic algebra, like trying to solve things you learned in algebra, and just continuing that story is where it leads you to like the frontier of math, where math is still alive and active and searching for new things. But we'll start again with the pictures. Let me stop it here.